Look up at the night sky. What you see is just a tiny fraction of reality. Stars, galaxies, even the vast cosmic web. All of it adds up to less than 15% of what the universe is actually made of. So where's the rest? 85% of everything is missing, invisible, utterly undetectable by any telescope or instrument we've built. This isn't science fiction. This is the biggest unsolved mystery in physics today. Scientists call it dark matter and dark energy, shadowy forces shaping the cosmos in ways we barely understand. Some think it's made of ghostly particles that pass through you right now without a trace. Others believe our laws of gravity are completely wrong, and a few even suspect we're living inside a cosmic simulation with the missing mass as a glitch in the code. Over the next 30 theories, we'll unravel these mind-bending ideas from ancient black holes to hidden dimensions and ask the ultimate question: what is the universe really made of? Strap in, this journey goes far beyond what your eyes can see. Now, let's dive into the first and perhaps most popular theory: dark matter particles. Imagine an invisible ocean filling the universe, made up of particles so elusive they pass right through planets, stars, and even you without a single interaction. These are weakly interacting massive particles, or WIMP for short. Scientists believe they could be the hidden architects of the cosmos, shaping galaxies in ways ordinary matter simply can't. Here's how it works. When astronomers measure how fast stars orbit the centers of galaxies, they find something bizarre. The outer stars move just as fast as the inner ones. But according to Newton's laws, without some unseen mass holding them in place, those outer stars should be flung into deep space. That's where WIMP come in. These hypothetical particles don't emit, absorb, or reflect light, making them completely invisible. Yet their sheer mass, somewhere between 10 and 1,000 times heavier than a proton, could create the gravitational glue that keeps galaxies from flying apart. The hunt for WIMP is one of the most thrilling detective stories in modern physics. Deep underground, in abandoned mines and beneath mountains, scientists have built ultra-sensitive detectors hoping to catch a rare collision between a WIMP and an ordinary atom. So far, no definitive proof has been found, but the search continues. If WIMP are real, they wouldn't just solve the mystery of missing mass, they'd open a window into an entirely new layer of reality, one where most of the universe has been hiding in plain sight all along. Now, let's shift our gaze to another intriguing candidate in the hunt for dark matter actions. Picture this: instead of heavy, sluggish particles like WIMP, imagine a universe filled with an almost ghostly mist of ultralight particles, each billions of times lighter than an electron. That's the essence of the action, a theoretical particle born not from the need to explain dark matter, but from an entirely different cosmic puzzle. Actions emerged from the minds of physicists trying to solve a mystery in quantum physics known as the strong charge parity problem. In simple terms, the equations governing the forces inside atomic nuclei seem to suggest certain symmetries should be broken, yet in reality they aren't. To fix this, scientists propose the action of particles so subtle it barely interacts with ordinary matter. But here's the twist: while actions were initially imagined to tidy up particle physics, they also turned out to be a perfect fit for dark matter. Unlike WIMP, which rely on their sheer mass to tug on galaxies, actions could form a diffuse, wave-like fog permeating space. Their incredibly low mass means they'd behave more like a field than individual particles, oscillating in ways that could collectively generate the gravitational effects we attribute to dark matter. Think of it like the hum of a vast, invisible choir, each voice too faint to hear alone, but together they create a force that shapes the cosmos. The search for actions is just as fascinating as the hunt for WIMP, but it's a different kind of challenge. Instead of underground detectors, scientists are building ultra-sensitive instruments designed to catch the faintest whispers of actions converting into photons in strong magnetic fields. Experiments like the Action Dark Matter experiment are pushing the boundaries of what we can detect, tuning their instruments like cosmic radios searching for the right frequency. If actions exist, they'd be more than just dark matter. They'd be a bridge between the quantum world and the large-scale structure of the universe. From solving a subatomic puzzle to potentially accounting for the missing mass of the cosmos, actions remind us that sometimes the answers to the universe's biggest mysteries might be hiding in the smallest, most unexpected places. Now, let's take a step back and question the very foundation of our understanding of gravity. What if the missing mass isn't missing at all? What if, instead of invisible particles, the answer lies in rewriting the rules of gravity itself? That's the bold idea behind modified Newtonian dynamics, or MOND for short. Unlike theories that rely on dark matter, MOND proposes that gravity doesn't behave the way Newton and later Einstein taught us when it comes to the vast scales of galaxies. At the heart of this idea is a simple but radical suggestion. Gravity might get stronger at extremely low accelerations, like those found in the outer edges of galaxies. This tweak could explain why stars on the fringes of galaxies rotate faster than expected without invoking dark matter at all. The story of MOND begins with astronomer Mordechai Milgrom in the early 1980s. He noticed something peculiar about galaxy rotation curves, the way stars orbit the centers of galaxies. According to Newton's laws, stars farther out should move slower, just like planets farther from the sun. But observations showed the opposite. These stars were moving just as fast as those closer in, as if some unseen mass was holding them in place. Instead of adding dark matter to the equation, Milgrom wondered, what if gravity itself was the variable? MOND introduces a critical threshold, a tiny acceleration below which gravity's behavior changes. Above this threshold, Newton's laws hold true, explaining everything from falling apples to planetary orbits. But below it, gravity gains a subtle boost, enough to account for those puzzling galactic rotations. It's like discovering that the rules of a game change slightly when you play on a much larger field. Of course, MOND isn't without its challenges. While it elegantly explains galaxy rotations, it struggles with other cosmic phenomena, like the gravitational lensing observed in galaxy clusters, which seems to require extra mass. Critics argue that dark matter still provides a more comprehensive solution across all scales. Yet, MOND remains a fascinating alternative, a reminder that sometimes the most revolutionary answers come from questioning the assumptions we take for granted. So, is gravity the real culprit behind the universe's missing mass, or is dark matter still the leading player? The debate is far from settled, but MOND keeps the conversation thrilling, proving that even the most established laws of physics are open for reinterpretation. Now, let's turn our attention to another intriguing possibility. What if the universe's missing mass isn't made of exotic particles or rewritten gravity, but of ancient black holes lurking in the cosmic shadows? This is the premise behind primordial black holes, hypothetical remnants from the universe's earliest moments that could be hiding in plain sight. Unlike the black holes we're familiar with, which form from collapsing stars, primordial black holes are thought to have emerged in the chaotic conditions just after the Big Bang. Tiny fluctuations in density could have created regions so dense they collapsed directly into black holes, some as small as an atom or as massive as a star. If these objects exist in large numbers, they could collectively account for the gravitational effects we attribute to dark matter. The beauty of this theory lies in its simplicity. Primordial black holes wouldn't require new physics or undiscovered particles, just ordinary gravity from invisible cosmic objects. But how do we find something that emits no light? The answer lies in a phenomenon called microlensing. When a primordial black hole passes in front of a distant star, its gravity bends and magnifies the star's light, creating a temporary brightening that telescopes can detect. These fleeting events could be the fingerprints of these elusive objects, Over the years, astronomers have searched for microlensing signals with mixed results. Some observations, like those from the Ogle project, have spotted events consistent with small black holes, but not enough to explain all the missing mass. Others suggest primordial black holes would disrupt star clusters or alter the cosmic microwave background in ways we haven't seen. Still, the idea remains compelling, especially for black holes in the so-called Goldilocks mass range, not too small to have evaporated by now, and not too large to have left obvious scars on the universe. Could primordial black holes be the dark matter we've been searching for? It's a tantalizing thought, blending the familiar with the mysterious. While the evidence isn't conclusive, the hunt for these ancient relics continues, reminding us that sometimes the answers to the universe's biggest puzzles might be hiding in the echoes of its birth. Now, let's explore a different corner of the cosmic puzzle. What if the missing mass isn't hiding in black holes or exotic particles, but in a ghostly cousin of a particle we already know? Enter sterile neutrinos, a hypothetical twist on one of nature's most elusive particles. Neutrinos are famously shy. They barely interact with matter, passing through entire planets like they're not even there. But sterile neutrinos take this aloofness to another level. Unlike ordinary neutrinos, which at least occasionally bump into other particles via the weak nuclear force, sterile neutrinos would interact only through gravity, making them nearly impossible to detect directly. That's exactly what makes them a compelling dark matter candidate. The idea hinges on neutrino oscillations, the bizarre phenomenon where neutrinos switch between different types electron, muon, and tau as they travel. Experiments like Mini-BU-NE and LSND have spotted anomalies in these oscillations that could hint at a fourth, sterile neutrino lurking in the shadows. If these particles exist, they'd be heavier than ordinary neutrinos but still incredibly light, potentially forming a diffuse sea of dark matter throughout the cosmos. One of the most intriguing aspects of sterile neutrinos is their potential to solve multiple mysteries at once. Beyond dark matter, they could explain why the universe has more matter than antimatter, a key imbalance that allowed everything we see to exist. They might also leave faint fingerprints in the cosmic microwave background or produce subtle X-ray signals when they decay, clues that telescopes like Chandra are actively hunting. Of course, the case isn't closed. Some experiments, like IceCube, have failed to find evidence for sterile neutrinos, while others see only tantalizing hints. The debate rages on, but that's the thrill of the hunt. Whether sterile neutrinos are the answer or just another red herring, they remind us that sometimes the universe's secrets are hidden in the smallest, most subtle details. And if they're real, these phantom particles could rewrite not just the story of dark matter, but our entire understanding of the subatomic world. Now, let's step into a world where every particle we know has a hidden twin, a cosmic symmetry so elegant it could unravel two of physics' biggest mysteries at once. This is supersymmetry, or SUSY for short, a theory that imagines a mirror universe of particles waiting to be discovered. At its heart, SUSY proposes that every known particle, electrons, quarks, photons, has a heavier superpartner with slightly different properties. For example, an electron superpartner would be the selectron, while a quarks would be the squark. These superpartners aren't just whimsical names, they could hold the key to dark matter. The lightest of them, often called the neutralino, wouldn't interact with light or ordinary matter much, making it a perfect candidate for the universe's missing mass. But SUSY isn't just about dark matter, it also tackles the hierarchy problem, one of particle physics' most puzzling questions: why gravity is so weak compared to other forces. In the standard model, this imbalance makes no sense, but SUSY superpartners could neatly cancel out the mathematical quirks that cause it, like cosmic counterweights restoring balance to the equations. The catch: despite decades of searching, no superpartners have been found. Colliders like the Large Hadron Collider have hunted for them, and while SUSY predicts they should appear at energies we've already probed, the detectors remain silent. Some theorists argue we might need even higher energies, while others suggest SUSY particles could be hiding in ways we haven't yet imagined. Yet SUSY elegance keeps it alive. It's a theory that feels almost too beautiful to be wrong, weaving together dark matter, gravity, and quantum physics into a single framework. Whether it's a groundbreaking truth or a near miss, SUSY reminds us that sometimes the most compelling answers lie just beyond the edge of what we can see, for now. Now, let's shift gears to a theory that ties two cosmic mysteries into one elegant package: dark fluid. Imagine if dark matter and dark energy weren't separate entities at all, but different faces of a single, exotic substance that changes its behavior as the universe evolves. That's the bold idea behind dark fluid, a model that could simplify our understanding of the cosmos. At its core, dark fluid behaves like a chameleon. In the early universe, when matter was densely packed, it acted more like dark matter, clumping around galaxies and providing the gravitational glue to hold them together. But as the universe expanded and matter spread out, this fluid's properties shifted. It began to repel rather than attract, mimicking the effects of dark energy and driving the accelerated expansion we observe today. What makes this theory so compelling is its simplicity. Instead of inventing two entirely unknown components to explain cosmic phenomena, dark fluid suggests one adaptable substance does the job of both. Think of it like water, sometimes a liquid, sometimes a vapor, but always H2O. Similarly, dark fluid's density and pressure could change over time, altering its gravitational effects without requiring new particles or forces. Of course, challenges remain. Critics point out that dark fluid must precisely match observations of both galaxy rotation curves and cosmic acceleration, a tall order. Some versions of the theory also struggle to explain why the fluid's transition from dark matter-like to dark energy-like behavior aligns so neatly with the universe's current age. Yet, if proven, dark fluid could be a game-changer, revealing a deeper unity behind the cosmos' greatest puzzles. Up next, we'll dive into an even more radical idea, where the fabric of spacetime itself might hold the key to dark matter. But for now, dark fluid stands as a reminder that sometimes the most elegant solutions lie in seeing connections where others see separations. Now, let's venture into the quantum realm, where the very fabric of spacetime might hold the answer to dark matter's mystery. Picture the universe at its smallest scales, not as smooth and orderly, but as a bubbling, frothy chaos known as quantum foam. This turbulent sea of spacetime, constantly fluctuating at distances a billion times smaller than an atom, could be the hidden source of the gravitational effects we attribute to dark matter. The idea hinges on Einstein's revelation that spacetime isn't just a static stage, it's dynamic, warping and twisting under the influence of matter and energy. Quantum mechanics takes this further, suggesting that at microscopic scales, spacetime is a storm of virtual particles popping in and out of existence. These fleeting disturbances might collectively create subtle gravitational pulls, mimicking the presence of unseen mass. Think of it like the surface of a boiling pot of water. From a distance, it looks calm, but up close, bubbles constantly form and collapse. If those tiny bubbles could tug on objects nearby, they'd create effects similar to dark matter's gravitational grip on galaxies. Quantum foam proposes that spacetime's microscopic turbulence does exactly that, acting as an invisible scaffold shaping the cosmos. Critics argue that these quantum fluctuations are too small to account for dark matter's large-scale influence. But some theories suggest that under extreme conditions like near black holes or in the early universe, these effects could amplify, leaving detectable imprints. Experiments aiming to measure spacetime's granularity, like advanced gravitational wave detectors, might one day reveal whether quantum foam is more than just a tantalizing what if. Up next, we'll stretch our imagination even further into the realm of extra dimensions, where dark matter might be hiding in plain sight just beyond our perception. But for now, quantum foam reminds us that sometimes the answers to the universe's biggest puzzles are written in the smallest whispers of reality. Now, let's take a leap beyond the familiar three dimensions and explore a mind-bending possibility. What if dark matter isn't missing at all, but simply lurking in dimensions we can't see? String theory, the ambitious framework aiming to unify all forces of nature, proposes that our universe might have more than just the three spatial dimensions we experience daily. In fact, it suggests there could be as many as 10 or 11 dimensions curled up so tightly that they're invisible to us. Here's where it gets fascinating. If these extra dimensions exist, some of the universe's matter, what we perceive as missing mass, might actually be bleeding into them. Imagine our three-dimensional world as a sheet of paper. Now picture tiny, unseen folds in that paper where particles could slip into higher dimensions, interacting with our world only through gravity. That gravitational tug would explain why we detect dark matter's influence but can't see it directly. This idea isn't just speculative math. Certain versions of string theory predict the existence of Kaluza-Klein particles vibrations in these extra dimensions that could manifest as heavy, stable particles in our 3D space. If these particles exist, they'd be perfect dark matter candidates, invisible yet gravitationally significant. Experiments like the Large Hadron Collider are hunting for hints of extra dimensions, searching for energy that seemingly disappears, potential evidence of particles escaping into higher realms. Of course, skeptics point out that extra dimensions remain unproven, and their connection to dark matter is still theoretical. But if future experiments uncover even indirect evidence, like anomalies in gravity at microscopic scales, it could revolutionize our understanding of reality itself. For now, the idea invites us to ponder a universe far stranger than we've imagined, where the answers to cosmic mysteries might lie just beyond the edges of our perception. Up next, we'll dive into an even more speculative twist: the possibility of an entire mirror universe, complete with its own invisible particles, silently shaping the cosmos alongside ours. Now, let's venture into one of the most intriguing possibilities. What if dark matter isn't just hidden in our universe, but part of an entirely separate one? Picture a mirror universe, a perfect cosmic twin where everything, particles, forces, even entire galaxies, exist just beyond our perception, invisible yet eerily similar to our own. This idea, known as mirror matter theory, suggests that alongside our familiar world, there's a parallel reality made of particles that interact only through gravity. Think of it like a ghostly echo of our universe, where mirror protons, mirror electrons, and even mirror stars and planets exist, but they don't emit light or collide with ordinary matter. The only way we'd notice them, their gravitational pull. That's where dark matter comes in. These invisible mirror particles could be the missing mass tugging on galaxies and bending spacetime. The beauty of this theory lies in its symmetry. Just as your reflection mimics your movements, mirror matter would follow the same physical laws as ordinary matter, just in its own hidden realm. Some models even propose that mirror particles could have formed mirror atoms, mirror chemistry, or even mirror life, though we'd never know since light from their world wouldn't reach ours. But how could we test such a wild idea? Scientists have looked for subtle gravitational anomalies or rare interactions between mirror particles and ours. For instance, if a mirror neutron occasionally tunneled into our universe, it might decay in ways that defy ordinary physics. Experiments like neutron beam studies have hunted for these oddities, though nothing conclusive has turned up yet. Critics argue that mirror matter feels more like science fiction than testable science, but its elegance keeps it alive. If true, it would mean our universe is just half of a grander cosmic duality, with dark matter as the shadow of a hidden twin. Up next, we'll explore a different twist: dark matter that doesn't just sit quietly in halos, but actively collides with itself, leaving clues in violent cosmic crashes. Now let's shift gears to a theory where dark matter isn't just lurking in the shadows, it's actively making its presence known through cosmic smash-ups. Imagine dark matter particles that don't just pass through each other like ghosts, but actually collide, leaving behind clues in the wreckage of galactic collisions. This is the heart of self-interacting dark matter theory. Take the famous bullet cluster, for example. When two galaxy clusters slammed into each other, something bizarre happened. The visible gas, hot and glowing, got stuck in the middle like cosmic traffic jam. But the bulk of the mass detected through gravitational lensing kept right on going, as if something invisible had sailed straight through. This mismatch suggests that most of the mass, the dark matter, didn't slow down or scatter the way ordinary matter did. If dark matter particles interact with each other, even weakly, they could explain this behavior. Picture two clouds of dark matter passing through one another, occasionally bumping and nudging, but mostly slipping past like crowds in a busy train station. These subtle interactions could create detectable distortions in how dark matter distributes itself after a collision. Some models propose that dark matter might have its own dark force, a hidden version of electromagnetism that lets particles push or pull on each other without affecting ordinary matter. If true, this would mean dark matter isn't just a passive bystander. It could have a rich, invisible dance of its own, shaping galaxies in ways we're only beginning to understand. Of course, not all collisions fit this picture perfectly. Some galaxy clusters show dark matter behaving more like a frictionless fluid, raising questions about how often these interactions really happen. But the hunt is on. By studying more cosmic crashes, astronomers hope to spot patterns that could reveal whether dark matter is truly social, or if it prefers to stay solitary. Up next, we'll explore another twist in the dark matter saga. What if it's not cold and heavy, but warm and lightweight, with particles that zip through the cosmos at surprising speeds? Now, let's turn our attention to a theory that flips the script on dark matter's weight class. What if the missing mass isn't made of sluggish, heavyweight particles, but something lighter and faster? Enter warm dark matter, the nimble contender in the cosmic arena. Unlike its cold counterpart, which moves slowly due to its massive size, warm dark matter consists of lighter particles, think keV scale, a fraction of the heft of traditional candidates. These particles zip through space at higher speeds, leaving a distinct fingerprint on the universe's structure. One of the biggest clues comes from the way galaxies form. Cold dark matter predicts a universe teeming with countless small satellite galaxies around larger ones, but observations show far fewer than expected. Warm dark matter could explain this discrepancy. Here's why. The faster-moving particles smooth out small-scale clumps of matter in the early universe, acting like a cosmic blender that prevents tiny galaxies from forming. Instead, they favor larger structures, aligning better with what we actually see in the cosmos. Picture trying to build a sandcastle with fine grains versus coarse sand. The finer particles create smoother, more uniform structures, while the coarse ones leave gaps. Warm dark matter works similarly, erasing the smallest bumps in the density of the early universe. The leading candidate for warm dark matter, sterile neutrinos, hypothetical cousins of the ordinary neutrinos we know, but with just enough mass to fit the keV scale. These particles wouldn't interact via the weak force like regular neutrinos, making them even harder to detect. Yet, their presence could solve multiple puzzles, from galaxy counts to the odd distribution of matter in cosmic voids. But warm dark matter isn't without its challenges. Some simulations suggest it might struggle to explain the very largest structures in the universe, like galaxy clusters. It's a delicate balancing act: too light, and it smooths out; too much, too heavy, and it behaves like cold dark matter again. As researchers refine their models and telescopes peer deeper into the cosmos, the debate between cold, warm, and even hot dark matter continues to evolve. Up next, we'll dive into another hidden player in this cosmic drama, dark photons, and how they might bridge the gap between dark matter and the forces we know. Now, let's explore a theory that could reveal an invisible hand guiding the universe's hidden mass. Imagine if dark matter doesn't just sit silently in the shadows, but actually communicates through its own secret force. This is where dark photons come into play, a mysterious messenger particle that might bridge the gap between the dark and visible worlds. Unlike the photons we know, which carry light and electromagnetic forces, dark photons would operate in a hidden sector, interacting only weakly with ordinary matter. Think of them as cosmic translators, facilitating conversations between dark matter particles while remaining nearly undetectable to us. If they exist, they could explain why dark matter seems so aloof, only making its presence known through gravity. The hunt for dark photons is on, with experiments like those at CERN searching for their faint signatures. Scientists use powerful particle accelerators to probe energy ranges where these elusive particles might appear. The idea is that if dark photons exist, they could occasionally mix with regular photons, leaving behind subtle traces in particle collisions. It's like tuning a radio to a frequency just outside the standard stations. You might catch whispers of a hidden broadcast. One intriguing possibility is that dark photons could also explain certain anomalies in particle physics, like the unexpected magnetic properties of some particles. If dark photons mediate a force between dark matter particles, they might indirectly influence the behavior of ordinary matter in ways we're only beginning to understand. But here's the catch: dark photons, if they're real, would be incredibly shy. They'd interact so weakly with normal matter that detecting them requires extreme precision and patience. Experiments have to sift through mountains of data, looking for the tiniest deviations that might signal their presence. So far, no definitive evidence has been found, but the search continues, fueled by the tantalizing prospect of unlocking one of the universe's biggest secrets. As we push the boundaries of particle physics, dark photons remain a compelling piece of the puzzle, a potential key to understanding how dark matter shapes the cosmos. Next up, we'll venture into the realm of supergravity, where another exotic particle, the gravitino, could hold the answer to the missing mass mystery. Now, let's shift our gaze to the elegant world of supergravity, where particles dance to the tune of hidden cosmic forces. Picture this: what if the missing mass of the universe isn't just hiding in the shadows, but is actually tied to the very fabric of spacetime itself? Enter gravitinos, theoretical particles that could be the missing link between gravity and dark matter. Gravitinos emerge from the realm of supergravity, a framework that blends Einstein's theory of general relativity with the principles of supersymmetry. In this elegant theory, every known particle has a heavier, unseen superpartner. The graviton, the hypothetical particle that carries gravity, would have its own superpartner, the gravitino. If these particles exist, they could have formed in the extreme conditions of the early universe, surviving as stable relics to this day. That means the dark matter we've been searching for might actually be a sea of gravitinos, quietly shaping galaxies with their gravitational pull. Here's where it gets fascinating. Gravitinos would be incredibly massive compared to other dark matter candidates, potentially weighing in at thousands of times the mass of a proton. Their sheer heft means even a small number of them could account for the universe's missing mass. But there's a catch: their interactions would be extraordinarily weak, making them nearly impossible to detect directly. It's like trying to spot a whisper in a hurricane. Scientists have proposed that gravitinos might leave indirect clues, though. If they decay over cosmic timescales, they could produce faint bursts of high-energy radiation. Telescopes scanning the skies for unexplained gamma-ray signals might one day catch a glimpse of these elusive particles. Another possibility is that gravitinos could subtly influence the formation of large-scale cosmic structures, leaving a unique fingerprint in the way galaxies cluster together. Yet, despite their promise, gravitinos remain purely theoretical. Supersymmetry, the grand framework that predicts their existence, hasn't been confirmed by experiments like the Large Hadron Collider. That doesn't mean gravitinos are off the table, it just means the hunt for evidence is tougher than we hoped. The beauty of this idea lies in its elegance, tying together gravity, particle physics, and cosmology in one sweeping theory. As we ponder the role of gravitinos, we're reminded that the universe's secrets often lie in the most unexpected places. Next, we'll journey even further back in time to explore remnants from the very dawn of existence, particles that might have formed when the cosmos was just a whisper of energy. Now, let's rewind the cosmic clock to the very beginning, when the universe was just a seething cauldron of energy. Imagine remnants so ancient and dense that they might hold the key to the missing mass puzzle. These are Planckian remnants, hypothetical fragments left over from the Planck epoch, the earliest moments after the Big Bang, when gravity and quantum mechanics were tangled in a dance beyond our current understanding. During this unimaginably brief period, the entire universe was compressed into a space smaller than an atom, with temperatures and energies so extreme that the laws of physics as we know them break down. If any structures or particles survived from this chaotic era, they would be unlike anything in our modern universe: ultra-dense, incredibly stable, and possibly invisible to our telescopes. Some theorists propose that these remnants could be the dark matter we've been searching for, lurking in the cosmos like cosmic fossils from the dawn of time. What makes Planckian remnants so intriguing is their potential to bridge two of physics' greatest mysteries: dark matter and quantum gravity. If they exist, they'd carry imprints of the universe's first moments, offering clues about how gravity behaves at the smallest scales. Picture them as tiny knots in spacetime itself, so dense that their gravitational pull could explain the missing mass without requiring new particles. They'd be like invisible anchors, subtly bending the paths of stars and galaxies without emitting a single photon. Of course, detecting these relics would be a monumental challenge. They'd likely be smaller than a proton, yet as massive as a mountain, making them nearly impossible to spot directly. But their presence might still leave traces, perhaps in the way they distort light from distant quasars or how they influence the cosmic microwave background. Some models even suggest that collisions between Planckian remnants could produce bursts of gravitational waves, offering a faint echo of their existence. While this idea remains speculative, it's a thrilling reminder that the answers to dark matter might lie not in the present, but in the universe's fiery infancy. Up next, we'll turn our attention to something closer to home: ordinary matter hiding in plain sight, waiting to be rediscovered. Now, let's shift our gaze from the cosmic extremes to something surprisingly familiar: ordinary matter that's been hiding right under our noses. While we've been chasing exotic particles and ancient remnants, some of the universe's missing mass might simply be ordinary stuff playing an elaborate game of hide and seek. Take brown dwarfs, for example. These celestial misfits are often called failed stars because they're too small to ignite nuclear fusion in their cores, yet too massive to be planets. They emit almost no light, making them incredibly hard to spot. Rogue planets wandering through space without a star to call home are equally elusive. And then there are vast clouds of cold gas drifting between galaxies, too faint for our telescopes to detect directly. Together, these could account for at least some of the missing baryonic matter, the ordinary protons and neutrons that make up everything we can see. But here's the twist: even though this matter is ordinary, it's far from easy to find. Traditional detection methods rely on light, but these objects are masters of stealth. Brown dwarfs glow faintly in infrared, while rogue planets and cold gas clouds are nearly invisible. Astronomers have had to get creative, using gravitational microlensing, where these objects briefly magnify the light of background stars, or hunting for subtle distortions in the cosmic microwave background. The idea that some dark matter could just be regular matter in disguise is both humbling and exciting. It reminds us that the universe still has plenty of ordinary tricks up its sleeve. Up next, we'll dive into a theory that ties dark energy to the very fabric of reality itself, the holographic principle. Now, let's explore a theory that bends the boundaries of reality itself, holographic dark energy. Imagine the universe as a cosmic projection, where everything we see and experience might just be information encoded on a distant, two-dimensional surface. This mind-bending idea comes from the holographic principle, which suggests that the three-dimensional world we perceive could be a kind of illusion, like a movie screen displaying a vast, intricate universe. So how does this connect to dark energy? If the universe's true structure is fundamentally informational, then the mysterious force accelerating cosmic expansion might not come from some exotic particle or field. It could emerge from the way information itself is stored and processed on that hidden boundary. Think of it like a computer running a simulation. The way data is organized and updated could create the appearance of an expanding universe, with dark energy as a side effect of the system's underlying rules. This theory elegantly ties together two of physics' biggest puzzles, dark energy and the nature of spacetime, by suggesting they're two sides of the same holographic coin. While still speculative, it offers a radical new way to think about the cosmos, where the missing mass and energy might not be out there in the traditional sense, but woven into the very fabric of reality's code. Up next, we'll examine another exotic contender, Chaplain gas, a strange cosmic fluid that could unify dark matter and dark energy in one mysterious package. Now, let's turn our attention to something truly bizarre: Chaplain gas, a cosmic fluid so strange it could hold the key to unifying dark matter and dark energy. Picture a substance that behaves like two entirely different things depending on when and where you look. In the early universe, when matter was densely packed, this exotic fluid would have acted like dark matter, clumping together under gravity to shape galaxies. But as the cosmos expanded and thinned out, its properties would shift, mimicking dark energy's repulsive force to drive the universe's accelerating expansion. What makes Chaplain gas so unusual is its pressure. Unlike ordinary fluids where pressure increases with density, this one does the opposite. Its pressure drops as it gets denser. It's as if you squeezed a sponge and instead of resisting, it became softer. This counterintuitive behavior lets it play both roles in cosmic history: a gravitational glue in the past and an anti-gravity push in the present. The elegance of this theory lies in its simplicity. Instead of inventing two separate mysteries, dark matter and dark energy, it suggests they might be different faces of a single, enigmatic substance. Of course, the challenge is proving it exists. Some researchers look for subtle imprints in the cosmic microwave background, while others study how galaxies cluster across time. If Chaplain gas is real, it would rewrite the cosmic rulebook, showing that the universe's missing mass isn't just hidden, it's shape-shifting. Coming up next, we'll dive into another radical idea: vortex dark matter, where galactic halos might not be made of particles at all, but swirling quantum whirlpools in an invisible superfluid. Now, imagine a universe where dark matter isn't made of particles at all, but instead, it's a cosmic superfluid swirling with invisible whirlpools. This is the mind-bending idea behind vortex dark matter. Picture a vast, invisible ocean filling the cosmos, where galaxies are like ships floating on its surface. But instead of water, this ocean is a quantum field, and its ripples and eddies create the gravitational effects we attribute to dark matter. The key here is superfluid dynamics. In everyday fluids like water, vortices eventually fade due to friction. But in a superfluid, a state of matter with zero viscosity, these whirlpools can persist indefinitely, forming stable structures. If dark matter is such a superfluid, its vortices could naturally explain the halos around galaxies. These swirling patterns would exert gravity just like particle-based dark matter, but without needing any undiscovered particles. What makes this theory so compelling is how it tackles one of dark matter's biggest puzzles: why galactic halos appear so smooth and evenly distributed. Particle-based dark matter struggles to explain this, but a superfluid's natural tendency to spread evenly could solve it elegantly. Some models even suggest that tiny quantum effects in this superfluid might alter gravity on galactic scales, bridging the gap between dark matter and modified gravity theories. Of course, testing this idea isn't easy. Scientists are looking for unique gravitational lensing patterns or subtle distortions in galaxy rotations that might betray the presence of these invisible vortices. If proven, vortex dark matter wouldn't just rewrite the dark matter story, it would reveal a universe far more fluid and dynamic than we ever imagined. Up next, we'll explore another twist in the dark matter saga, Kaluza-Klein dark matter, where hidden dimensions might hold the missing pieces of the cosmic puzzle. Now, let's stretch our imaginations beyond the familiar 3 dimensions and into the hidden folds of the cosmos. Kaluza-Klein dark matter takes us into the realm of extra dimensions, where the very fabric of reality might hold the answer to the universe's missing mass. Picture this: what if dark matter isn't just lurking invisibly in our 3-dimensional space, but is actually vibrating in dimensions we can't even see? This theory builds on the work of physicists Theodore Kaluza and Oskar Klein, who proposed that gravity and electromagnetism could be unified if our universe had an extra, curled-up dimension. Fast forward to today, and their idea has evolved into a stunning possibility. Dark matter could be particles that are, in a sense, echoes of higher dimensional vibrations. These particles, known as Kaluza-Klein states, would appear massive and stable in our 3-dimensional world, making them perfect candidates for dark matter. Here's how it works. In extra-dimensional theories, particles moving through higher dimensions would have additional momentum, which we'd perceive as extra mass in our 3-dimensional slice of reality. These Kaluza-Klein particles wouldn't interact with light or ordinary matter, just like traditional dark matter, but their origins would be far more exotic. Some models even suggest that the lightest of these particles could be stable enough to survive from the Big Bang to today, filling the cosmos with invisible mass. What's fascinating is how this idea ties into string theory, where multiple extra dimensions are a core feature. If Kaluza-Klein dark matter is real, it wouldn't just solve the missing mass problem, it would be a smoking gun for the existence of higher dimensions themselves. Experiments like the Large Hadron Collider are searching for hints of these particles, though detecting them would require piercing the veil of our dimensional reality. Up next, we'll challenge the very stability of dark matter. What if it's not eternal, but slowly fading away? Stay tuned as we dive into the intriguing possibility of dark matter decay. But what if dark matter isn't as permanent as we've always assumed? Let's explore a twist in the cosmic tale, dark matter decay. For decades, scientists have treated dark matter as a stable, unchanging presence in the universe, silently shaping galaxies without ever fading away. But what if that's not the whole story? This theory dares to question dark matter's immortality, proposing that it might slowly disintegrate over cosmic time. Imagine dark matter particles breaking down into something we can detect, like photons or neutrinos, leaving behind faint traces of their existence. If true, this decay could solve 2 mysteries at once: the missing mass problem and the unexplained excess of high-energy radiation humming through space. Here's where it gets exciting. Gamma-ray telescopes like NASA's Fermi Space Telescope are scanning the skies for these ghostly signals. Certain regions, like the centers of galaxies where dark matter is densest, should glow with excess gamma rays if decay is happening. Some observations have even spotted tantalizing hints, unexplained spikes of energy that could be dark matter's final whisper. Skeptics argue these could be pulsars or other astrophysical phenomena, but the hunt is far from over. The implications are staggering. If dark matter decays, it means the universe's invisible scaffolding is slowly eroding. Over billions of years, this could alter the fate of galaxies, even the cosmos itself. It's a reminder that the universe is never static. Even its most mysterious components might be playing a slow-motion game of hide and seek with us. Now, let's shift gears to a theory that rewrites gravity itself. What if dark matter isn't a particle at all, but a sign that our understanding of gravity is incomplete? Next up, we'll unravel the bold ideas behind emergent gravity. Now, let's step into a mind-bending idea that turns gravity itself upside down. What if the force holding galaxies together isn't caused by invisible matter at all, but by something far more fundamental, the very fabric of information in the universe? This is the radical premise of emergent gravity, a theory pioneered by physicist Eric Verland. Verland's idea starts with a startling claim: gravity isn't a fundamental force like electromagnetism. Instead, it emerges from the way information is arranged in spacetime, a concept rooted in entropy, the measure of disorder in a system. Think of it like this. When you push your hand through water, the resistance you feel isn't because of some hidden substance. It's the collective behavior of countless water molecules. In the same way, Verland suggests gravity is a side effect of how the universe organizes itself at the deepest level. This theory throws dark matter out of the equation entirely. According to emergent gravity, the strange motions of stars in galaxies, the very phenomenon that led us to propose dark matter, aren't due to invisible particles. They're the result of spacetime's hidden elasticity, a kind of cosmic tension that mimics the effects of extra mass. It's as if the universe has been playing a trick on us, making us invent dark matter when the real explanation was hiding in plain sight. The implications are profound. If Verland is right, our entire understanding of gravity, from Newton's apple to Einstein's warped spacetime, needs a rewrite. But here's the catch. While emergent gravity elegantly explains galactic rotation without dark matter, it struggles with larger scales like galaxy clusters. Critics argue it's not yet a complete replacement, but a tantalizing hint that we might be missing something even bigger. So where does this leave us? In a universe where gravity could be an illusion and dark matter a cosmic mirage, next we'll dive into another twist, a theory where dark matter isn't a particle or a gravity glitch, but a wave-like entity so light it defies intuition. Now let's shift gears to a theory that takes dark matter into the realm of the bizarrely tiny. Picture this: what if dark matter isn't made of heavy, sluggish particles, but instead consists of featherweight waves so light they barely register? This is the essence of fuzzy dark matter, a theory that reimagines the missing mass as an ocean of ultra-light particles, each with a mass so small it's almost laughable, around 10 to the power of -22 electron volts. At this scale, quantum mechanics takes center stage. These particles wouldn't behave like discrete dots but as sprawling waves, their interference patterns weaving through galaxies like ripples in a pond. This wave-like nature could solve one of dark matter's biggest puzzles: why small galaxies and star clusters don't seem to have as much dark matter as models predict. Fuzzy dark matter's waves would naturally smooth out on small scales, suppressing the formation of overly dense clumps. A neat fix for these galactic anomalies. But here's where it gets even stranger. Because these particles are so light, their wavelengths could stretch across entire galaxies. Imagine a single particle's wave stretching from one end of the Milky Way to the other, its gentle undulations subtly shaping how stars orbit. It's a far cry from the traditional image of dark matter as a swarm of invisible baseballs. Instead, think of it as a cosmic fog, its delicate quantum fingerprints etched into the motions of every star. Of course, fuzzy dark matter isn't without its challenges. For one, how do particles this light even arise in the early universe, and can they truly account for all the gravitational effects we see? While experiments are still catching up, the theory offers a thrilling reminder: dark matter might not just be invisible. It might be fundamentally weird, blurring the line between particle and wave in ways we're only beginning to grasp. Up next, we'll explore an even more exotic idea: dark matter that doesn't just hide in the shadows, but forms intricate, invisible structures of its own. Now, let's venture into a theory that gives dark matter an eerie mirror of our own atomic world. Imagine if dark matter isn't just a sea of solitary particles, but forms entire atoms, complete with their own invisible protons, electrons, and even a shadowy version of electromagnetism. This is the idea behind dark atoms, a theory that suggests the missing mass could be hiding in complex, ghostly structures we can't see. Think of it like this. In our visible universe, ordinary atoms are built from protons and electrons bound together by electromagnetic forces. Dark atoms propose a parallel reality where dark protons and dark electrons exist, tied together by a mysterious dark electromagnetism. These particles wouldn't interact with light, but their gravitational pull would still shape galaxies and galaxy clusters just like traditional dark matter. The difference, instead of floating freely, they'd clump into intricate, invisible molecules or even larger formations, structures we'd never notice unless we felt their gravity. This theory could explain some puzzling observations. For instance, certain gravitational lensing patterns, where light bends around massive objects, suggest dark matter might be more lumpy than expected. If dark atoms form clusters or filaments, they could create these subtle irregularities in space-time. It's like finding footprints in the snow. You can't see the creature that made them, but the marks hint at something complex moving through the darkness. But here's the catch: if dark atoms exist, why haven't we detected them? The answer lies in their neutrality. Just as regular atoms are electrically neutral overall, dark atoms would lack any charge we can measure, making them nearly impossible to spot with current tools. Some experiments are searching for faint traces, like rare collisions between dark atoms and ordinary matter, but so far the evidence remains elusive. What makes this idea so compelling is its elegance. It takes the familiar architecture of our universe and flips it into the shadows, suggesting that dark matter might not be so alien after all. Maybe it's just a hidden reflection of everything we already know. Up next, we'll unravel another cosmic mystery: dark matter woven into the fabric of spacetime itself, not as particles, but as ancient defects left over from the birth of the universe. Now, let's stretch our imaginations even further beyond particles and atoms, to a theory where dark matter isn't made of matter at all, but of cosmic scars left over from the universe's fiery birth. Picture the early cosmos as a bubbling cauldron of energy, cooling rapidly as it expanded. Just like cracks forming in ice as it freezes, the fabric of spacetime itself might have developed flaws, one-dimensional rips called cosmic strings. These aren't the strings of string theory, but ultra-dense, spaghetti-thin filaments stretching across the universe, heavier than entire galaxies, yet no wider than a proton. What makes cosmic strings so fascinating is how they could mimic dark matter's effects without needing any exotic particles. Their immense mass would warp spacetime around them, bending light just like invisible matter does. Imagine dangling a heavy chain across a bedsheet. The fabric dips under its weight, distorting the surface. Cosmic strings would do the same to the universe, creating gravitational footprints that look like dark matter's handiwork. Some astronomers even speculate that these strings might explain strange, straight-line distortions seen in distant galaxy clusters, hints of invisible threads tugging at the cosmos. But here's the twist: unlike particle-based dark matter, cosmic strings would leave unique calling cards. As they vibrate or snap, they could send out bursts of gravitational waves, ripples in spacetime, that detectors like LIGO might one day catch. Others theorize that strings might create double images of galaxies as their gravity splits light like a prism. Yet despite decades of searching, no definitive proof has emerged. The challenge: cosmic strings would be so sparse that finding one is like spotting a single strand of spiderweb stretched between New York and Los Angeles. This idea forces us to rethink dark matter not as stuff, but as structure a relic of the universe's tumultuous infancy. Whether these cosmic scars exist or not, they remind us that the answer to the missing mass puzzle might be written in the wrinkles of spacetime itself. Coming up next, we'll explore a theory where dark energy isn't a constant force, but a dynamic field that evolves with the universe shaping its fate in ways we're only beginning to understand. Now, let's shift our focus to a theory that breathes life into the very fabric of the cosmos quintessence. Unlike the static force of dark energy we often imagine, quintessence proposes a dynamic, ever-changing field that evolves alongside the universe itself. Think of it as a cosmic chameleon, adapting its behavior over time rather than remaining a fixed constant. This idea challenges the traditional view of dark energy as a uniform, unchanging presence. Instead, quintessence suggests a scalar field, a kind of invisible energy fluid that fluctuates in density as the universe expands. Picture blowing up a balloon with patches of varying thickness. Some areas stretch more than others, creating an uneven push. Quintessence works similarly, its influence waxing and waning, potentially explaining why the universe's expansion rate doesn't always align with predictions. What makes quintessence especially intriguing is its potential interplay with dark matter. Some models suggest this dynamic field could interact with dark matter particles, subtly altering their behavior over billions of years. Imagine two dancers, one visible, one hidden, whose movements influence each other despite never touching. This interaction might solve lingering mysteries, like why certain galaxy clusters appear more spread out than expected. Yet quintessence isn't without its puzzles. If this field changes over time, why does its effect seem so uniform across the vast cosmos? And how do we distinguish its fingerprints from other dark energy candidates? Future telescopes like the Euclid mission aim to measure the universe's expansion with unprecedented precision, potentially revealing whether dark energy is a rigid constant or a shape-shifting force like quintessence. This theory invites us to see the universe not as a static stage but as a living, evolving entity, where even the forces driving its expansion might have their own hidden rhythms. Up next, we'll turn our attention to a heavyweight contender in the dark matter debate. The neutralino, a particle that once seemed destined to solve the mystery but has kept scientists waiting in suspense. Now, let's turn our attention to a particle that once held the spotlight as the leading candidate for dark matter. The neutralino. Born from the elegant framework of supersymmetry, or SUSY for short, the neutralino is a hypothetical heavyweight in the particle physics world. Imagine a mirror version of every known particle, each with a superpartner that balances the cosmic scales. The neutralino is one such superpartner, a stable and massive particle that doesn't interact with light, making it a perfect fit for the dark matter puzzle. For years, scientists were convinced the neutralino was the answer. Its stability and mass seemed tailor-made to explain the gravitational effects we see in galaxies. Picture a universe teeming with these invisible particles, silently shaping the cosmos without ever revealing themselves. The beauty of SUSY was that it didn't just solve the dark matter mystery, it also addressed other big questions in physics, like why the Higgs boson is so light compared to other particles. But here's the twist: despite decades of searching, colliders like the Large Hadron Collider haven't found a trace of the neutralino. You'd think a particle this important would have shown up by now, right? The absence of evidence has left physicists scratching their heads. Some wonder if SUSY particles are simply heavier than we thought, hiding just beyond the energy levels our current machines can reach. Others speculate that the neutralino might not exist at all, forcing us to rethink our assumptions. The hunt isn't over, though. Upgrades to particle colliders and new detection methods keep the hope alive. If the neutralino is out there, it's playing an epic game of hide and seek with science. And whether it's found or not, its story reminds us that even the most promising theories must face the ultimate test: reality. Next, we'll explore another fascinating idea: dark matter that isn't just invisible but might also form intricate crystalline structures across the universe. Now, let's venture into a theory that sounds like it's straight out of science fiction: dark matter crystals. Picture this: instead of being a chaotic sea of invisible particles, dark matter might actually form intricate, ordered structures, much like the crystals we see in nature. Imagine vast, cosmic lattices stretching across galactic halos, their precise arrangement subtly bending the light from distant stars in ways that could explain the strange gravitational lensing patterns astronomers observe. This idea flips the script on how we think about dark matter. Instead of loose, randomly scattered particles, it suggests dark matter could have a kind of solid phase, with particles locking into repeating patterns over enormous scales. Think of it like frost forming on a window, individual water molecules arranging themselves into delicate, symmetrical shapes. If dark matter behaves similarly, these crystalline structures could create the precise gravitational effects we've been struggling to explain. But how would such crystals form? One possibility is that certain types of dark matter particles interact weakly with each other, just enough to settle into stable, organized configurations over billions of years. These interactions wouldn't be like the strong bonds in everyday crystals, but something far more subtle, perhaps mediated by an unknown force unique to the dark sector. The real intrigue lies in the fingerprints these crystals would leave behind. If they exist, their orderly nature could produce distinct distortions in the light bending around galaxies, offering a way to test the theory. Astronomers are already scrutinizing gravitational lensing data for hints of these patterns, searching for the cosmic equivalent of a crystal's telltale sparkle. Of course, this is still speculative. No one has found definitive proof of dark matter crystals yet. But the possibility opens up a whole new way to imagine the invisible scaffolding of our universe, not as a formless fog, but as a grand crystalline architecture, quietly shaping the cosmos in ways we're only beginning to explore. Next, we'll question whether the very laws of physics themselves might be changing over time, challenging the need for dark matter altogether. Now, let's take a step into one of the most mind-bending possibilities. What if the laws of physics themselves aren't as constant as we think? For centuries, scientists have assumed that fundamental constants, like the gravitational constant big G, stay the same across space and time. But what if they don't? What if gravity was stronger in the past or weaker in certain parts of the universe? This idea could rewrite our understanding of dark matter entirely. Here's how it works. If the strength of gravity changes over time or across different regions of space, the strange motions of galaxies and galaxy clusters might not need dark matter to explain them. Instead, the math would simply reflect a universe where gravity behaves differently than we've assumed. Think of it like tuning a radio. If the dial shifts slightly, the signal changes. In this case, tweaking gravity's strength could make the need for invisible matter vanish. But how would such a change happen? Some theories suggest that extra dimensions, quantum effects, or even the expansion of the universe itself could subtly alter these constants. It's not an easy idea to test, but scientists have looked for tiny variations in things like the fine structure constant, a number that governs electromagnetism, by studying light from distant quasars. So far, the evidence is inconclusive, but the search continues. The real appeal of this theory is its elegance. Instead of inventing an entirely new form of matter, it asks whether we've misunderstood the rules all along. Of course, it's a radical departure from mainstream physics, and many researchers remain skeptical. But if true, it would mean that dark matter isn't missing. It was never needed in the first place. Up next, we'll push the boundaries even further with a theory that blurs the line between science and philosophy: the simulation hypothesis. Could our entire universe, with its unexplained mass, just be lines of unrendered code in a cosmic computer? Now, let's dive into the most provocative theory of all. one that challenges not just our understanding of dark matter, but the very nature of reality itself. What if our universe isn't the base reality, but an incredibly advanced simulation? This idea, known as the simulation hypothesis, suggests that missing mass might not be a physical substance at all. Instead, it could be a kind of cosmic oversight, unrendered code in the vast program running our simulated existence. Think of it like a video game where developers leave out details in distant areas to save processing power. In our universe, dark matter's gravitational effects might simply be the simulation's way of filling in gaps where full calculations aren't necessary. The strange behavior of galaxies, just a placeholder until the system renders them properly. It's a wild idea, but some physicists and philosophers take it seriously, arguing that if a civilization could create simulations indistinguishable from reality, the odds are high we're in one. Of course, this raises big questions. How could we ever test such a theory? Some suggest looking for tiny glitches in physical laws, like inconsistencies in energy levels or mathematical patterns in cosmic radiation. Others propose that if the universe is a simulation, it might have computational limits, hints of pixelation or frame rates in the fabric of spacetime itself. So far, no smoking gun has been found, but the search is as fascinating as the theory. The simulation hypothesis doesn't just redefine dark matter, it redefines everything. If true, it means the mysteries of the cosmos aren't just unsolved physics problems. They might be clues left by the programmers. Whether you find this idea thrilling or unsettling, one thing's certain: it pushes the boundaries of science and imagination further than any other theory we've explored. And with that, we've reached the end of our journey through 30 mind-bending theories about the universe's missing mass. From WIMP to simulations, each idea shows how creatively science tackles the unknown. Which theory resonates with you? Let us know in the comments, and don't forget to subscribe for more deep dives into the universe's greatest mysteries. Until next time, keep looking up and questioning everything. And so, we've traveled through a cosmos of ideas, each one a bold attempt to solve the universe's greatest missing piece. From the elusive WIMP hiding in the shadows of galaxies to the mind-bending possibility that our reality might be a simulation, these theories showcase something extraordinary: the limitless creativity of science when faced with the unknown. Whether it's invisible particles, twisted gravity, or even unrendered code, every hypothesis pushes the boundaries of what we think is possible. What's remarkable isn't just the diversity of these ideas, but the fact that they all exist because scientists refuse to settle for mysteries. They tinker, test, and imagine, turning the gaps in our knowledge into playgrounds for discovery. And that's the beauty of it. No single theory has to be right for the journey to be worthwhile. Now, we'd love to hear from you. Which of these 30 theories grabbed your imagination the most? Did the elegance of supersymmetry pull you in, or does the sheer audacity of the simulation hypothesis leave you questioning everything? Drop your thoughts in the comments below. Let's keep the conversation as vibrant as the cosmos itself. If you enjoyed this deep dive into the universe's hidden secrets, don't forget to hit that subscribe button and ring the notification bell. There are countless more mysteries waiting to be explored, from black holes to quantum oddities, and we'd love for you to join us on the next adventure. Until then, stay curious, keep wondering, and remember, the universe's greatest stories are still being written.